Understanding tens of minutes surgical videos requires long-horizon temporal reasoning. You need to answer questions about what happened before, after, or across different stages of a procedure, and you have to ground those answers in visual evidence that is scattered across time. Current systems struggle with this. A one-shot vision language model tries to ingest the entire procedure at once, compresses it to fit a context window, and immediately loses the fine-grained temporal detail that before or after questions depend on. On the other hand, video agents that train models to learn where to look require massive amounts of trajectory data, overfit to their training distribution, and transfer poorly to out-of-domain surgeries. That is precisely where the ability is most needed, and labeled data is scarcest. What if we could teach an AI to know where to look without updating a single weight? That is the core premise of MedClaw. Instead of optimizing parameters, the system improves by evolving context. It separates the reasoning from the perception. A text-only orchestrator plans the evidence-gathering strategy and issues an auditable sequence of tool calls, while frozen vision language subagents execute those calls over the raw pixels. Everything happens in context, turning the latent problem of temporal localization into an explicit, inspectable action trace. Let's break down how this harness actually works. The orchestrator never sees the video directly. It interacts with a fixed tool suite that enforces a strict coarse-to-fine localization strategy. First, it calls ViewFull Video to scan the entire procedure. This tool runs a low-resolution pass to emit a dense timeline of what is visible in each interval, and then a higher-resolution rewatch to pinpoint the tightest candidate window for the queried event. Once the orchestrator has a candidate region, it uses crop video to inspect what happens inside that range. If it needs to verify a specific instrument, anatomical structure, or surgical action, it drops down to select video frame or crop video frame for spatial disambiguation. It can also query an external surgical knowledge base using retrieval-augmented generation, pulling in PubMed abstracts and literature-grounded summaries to cross-reference terminology. Every single action is logged. The full trajectory is recorded, meaning you can trace exactly which frames, crops, and tools led to a conclusion. The vision tasks themselves are handled by frozen subagents. A video expert processes temporal segments, while a frame verifier handles single-image inspection. Neither is fine-tuned. So how does the system actually improve over time? Through a gradient-free, reward-gated loop called heuristic skill distillation. This loop starts by running the harness on a small mining set of roughly 100 labeled questions. When the agent fails to answer correctly, the orchestrator diagnoses the gap between its own output and the gold standard. It classifies the failure into one of three categories. An operational gap means the answer was present in the video, but a different-looking strategy would have caught it. An unreachable gap means the video literally doesn't contain the information, like off-screen narration or a pathology report. And a type C means the answer was already correct. Only operational gaps generate actionable lessons. The orchestrator writes those lessons into a candidate's skill, updating existing entries if they overlap, or creating new ones if they don't. But mining alone isn't enough. To prevent plausible but useless rules from accumulating, every candidate skill is strictly reward-gated. Before testing, we measure the baseline reward of the empty library on a validation set. We then install each candidate skill one at a time, re-answer the entire validation set, and measure the new reward. A skill is only retained if it raises the mean four-dimensional reward, correctness, detail, context, and temporal understanding, by a meaningful margin, and crucially it must not degrade any individual question by more than 2 points. This gating ensures a strategy is kept because it actually works, not because it looks theoretically sound. The loop converges on a compact, reusable skill library. The most impactful skill it discovers is called directed relook. For temporal questions, the answer rarely sits inside the window that depicts the named event. It sits in the adjacent window. Once the orchestrator localizes the event, the skill instructs it to crop and reread the preceding or following segment. The harness didn't hardcode this. It mined it from its own temporal mistakes, and the reward gate confirmed it actually lifts performance. You cannot evaluate this properly without a benchmark that actually isolates long-horizon reasoning. Most existing surgical QA datasets rely on shortcuts. They use short clips, contain spoken narration that states the answer aloud, allow answers from textbook priors, or can be solved from a single frame. MedClawBench fixes this. It is deleaked and doctor-grounded. It contains over 1,100 questions across long neurosurgery recordings and held-out public lecture videos. Every candidate question passes a strict filtering cascade. We enforce a minimum video duration of 10 minutes. We run a blind test where a text-only model without video access must fail to answer it. We run a local test where a model restricted to the target window must succeed, proving the answer is grounded in visual evidence, not a course overview. For lecture videos, we run a narration filter to discard questions answerable by audio alone. For the neurosurgery portion, we run a faithfulness check against expert interval annotations to ensure the gold labels aren't hallucinated textbook knowledge. The result is a benchmark that forces the model to actually watch and reason across time. On MedClawBench, the harness consistently outperforms one-shot vision language models and general video agent frameworks. The gains are especially pronounced on the long, out-of-domain neurosurgery videos, where temporal reasoning is most stressed. The ablations tell a clear story about what drives those gains. Removing the coarse-to-fine localization drops performance, proving that narrowing down from the whole procedure to the exact moment is necessary. But removing the distilled skills hurts the most, and within that, the directed relook skill accounts for the largest single drop in temporal understanding. The harness also lifts diverse frozen backbones, showing the architecture itself is driving the improvement, not just a stronger base model. And swapping the orchestrator shows graceful degradation rather than failure, proving the tool calling loop is robust across different reasoning policies. The clinical and technical implications here are significant. Because every retrieval step is an explicit tool call over unchanged weights, the evidence trace is fully inspectable. A researcher or clinician can review exactly where the agent attended, what crops it inspected, and how it derived its conclusion. And because adaptation happens through an external skill library rather than parameter updates, the system can be extended to new procedures or specialties using only a handful of examples. MedClaw doesn't just push numbers up on a benchmark. It demonstrates a fundamentally different way to build reasoning agents, by evolving context, mining failures, and keeping the model frozen. If you're working on long-form video understanding, medical AI, or agentic systems, this framework is worth a deep dive. I've linked the paper and project page in the description. Thanks for watching, and I'll see you in the next one.